And our last section in Chapter 2 will be Section 2.6, where we discuss water mixtures. Mixtures are going to be formed by combining two or more substances. There are two defining features. We have substances mixed that are not chemically changed, and substances that can be separated by physical means, such as doing things like evaporation or filtering. So let's look at the three categories of water mixtures. First, we have a suspension. This is when we have material that is larger in size than 1 millimeter mixed with water. Examples of this in our body would be like our blood cells within the plasma. So the plasma would be like your yellowish substance in here, or sand within water. And you could see that it does not remain mixed unless it's in motion. So I have the example of this glass of water with sand that has been mixed around, and you could see that it can form a cloudy or opaque type of solution, and it scatters light if it's shined through. The other type of mixture that we have is a colloid. This has smaller particles than the suspension, but larger than those in a solution. So examples in our body would be like fluid in the cell cytosol and fluid in our blood plasma. It's going to remain mixed when not in motion. So an example would be milk mixed with water. And here you could see if we shine a light through, you could see in the colloid that it is going to scatter light. And our last water mixture would be a solution. This is going to be a homogeneous mixture of a material smaller than 1 nanometer, and it will dissolve within water. So when we shine a light through a solution, it is not going to scatter light. We'll also see that the substance is not going to settle if the solution is not in motion. Examples would be like sugar water that we have over here, salt water, and blood plasma. And there's a special category of suspension, and this is emulsion. This is when we have water and a nonpolar liquid substance. Examples of this would be like oil and vinegar salad dressing or breast milk. And these substances are not going to mix unless it is shaken. And I have pictured for you some other examples here on the right-hand side. Here is a figure from your book also depicting some of the mixtures that we just discussed. Here we see suspension, in which we are looking at our blood in motion versus not in motion. Our colloid, which you can also compare to like jello or gelatin. And solution, where we see our smallest solutes are not scattering light or settling within this test tube. Another example of that would be like soda. And here's emulsion, where when we have our test tube in motion, the oil forms these little, almost like those missiles we saw in previous sections, whereas when it's not in motion, they separate out and we have that exclusion that is taking place. So how do we express a solution concentration? The concentration will be determined by the amount of solute, those particles that are dissolved in a solution. So we can express this as mass and volume. So our mass would be the solute per volume of solution. This is going to be represented as an example of your results from a blood test, or we can look at a mass volume percentage. So we take the grams of that solute and we divide it per 100 milliliter solution. So an example of that would be like an IV solution. And then we can use the terms molarity and molality to also discuss concentration. These terms are very similar, so I have some tips on the right-hand side for you to differentiate them. First, let's talk about molarity. These are going to be moles of the solute per liter solution. It's going to alter with changes in temperature, and it's more easily measured within our body than compared to molality. So we can remember this by remembering that molarity has only one L in its name. So we put that one L on the bottom of how we calculate molarity. When we talk about molality, this is going to be the moles solute over kilograms of the solvent. So we will see that this will not alter with changes in temperature, and it's slightly more accurate type of measurement in concentration than molarity, but it's difficult to attain this within the body. So if we look at the word molality, you see that it has two L's, so kind of think that these two L's cancel themselves out, so we are not going to put it on the bottom here, and instead we will put kilograms of the solvent. Now let's talk about another unit of measurement here. This is going to be osmoles, or we abbreviate it as OSM. This is a unit of measurement for the number of particles in a solution, and we'll be using this a lot, for instance, when we talk about the urinary system and looking at things like the salt concentration within our blood or within the medulla or our nephron tubules within the kidney. This is going to reflect whether a substance dissolves or dissolves and associates, and it can be expressed as osmolarity or osmolality. So here we have those similar looking terms again. Osmolarity is going to be the number of particles in the 1 liter solution. Once again, it's easier to measure, and our blood serum expresses as many osmoles. And osmolality is going to be the number of particles in 1 kilogram of water. Once again, it's more accurate, but it's difficult to measure. So what is a mole? We kept on talking about that when we discussed our molarity and molality. So our mole is going to be a fixed number. It is 6.022 times 10 to the 23rd atoms, ions, or molecules. And this is our mass in grams equal to atomic mass of an element or molecular mass of a compound. So 1 mole of carbon is going to be equal to 12.01 grams. And we are going to do some calculations in our lab using this number. So you should commit this to memory. To find molecular mass, we are going to multiply the number of units of each element by an average atomic mass, and then add the totals. So let's do an example of this. We have in water 2 hydrogens, so we do 2 multiplied by the 1.008, that equals 2.016, and we have 1 oxygen. So we do 1 times the mass of oxygen, which is 15.999, and we just took these numbers from your periodic table. That's going to equal 15.9999. Wait, I added an extra 9 there, didn't I? And so when we add these totals, we get our molecular mass, which is 18.015.